Okay, welcome back. We're on page 391 talking about the exclusive OR. And if you're a coder, you probably know about the logical, you know, an OR, an AND, or a NOT, and then exclusive OR is one of those a little more complicated. So it's basically used as like a logical operator, or it's being used as a bit manipulator. Anyway, it's rarely used by itself because it's not robust enough, but it could be used in the inside, the guts of some of the other algorithms. The Vernam Cipher. It's what's called a one-time pad. In other words, you use this text as sort of like a key, and you take the plain text plus the key, using a numeric from the ASCII character, and you roll them over, etc., etc., etc. So the other end would have to know what the pad text was, basically. So you kind of cool. Book-based ciphers. Okay, yet another movie reference. In the movie National Treasure, there have been several, but the first one, there's apparently a hidden message in the Silence Do-Good letters that Ben Franklin wrote. And so it goes like this. To make my message, I say, this King James Version Bible on page 42, line 4, letter 6. So it'd be page, line, letter. And so in the movie, they send this kid in to write down each letter one at a time. Anyway, this is actually very powerful because if you do not have the book, then there is no way you can tell what's going on. There's no analysis that's going to help here. None whatsoever. Because you're just not going to be able to figure it out. You have to have the book. Okay. So typically the page number, line number, and a word. So page 2, line 4, 8th word, that would work. I would just send you 2, 4, 8. That's it. And followed by another series of digits. So page, line, word. If the words work, otherwise they'd be letters. Anyway, extremely hard to crack if you don't know what book they're talking about. So if everyone in prison was assigned the exact same version Bible, okay? All you have to do is just go home and buy the exact same version that they hand out at the prison. And therefore, I can do secret messages to and from my prison person or vice versa. Cool? Okay. What's called a running key. It starts with a book cipher, but that just gets you the key, and then you switch over to the veneer. Okay. A template. This one is kind of cool. This one, what they would do is it kind of sort of like the page guy, but they would hold up a piece of paper and either cut a little hole in each one in strategic places, right? And then you place that piece of paper on over the page, and whatever letters showed up, it would do. Now, that's pretty doggone smart. Again, I have to have the exact same book you have. Or it could be something simple as an indentation. It doesn't have to be a hole, just an indentation. Or maybe just an innocent-looking little dot. Or maybe for some reason, I wrote the thing in red ink or, blue ink, but there's a couple of red dots or black dots on the page. And so, I basically hold it up to the page, and I can see what you're talking about. Kind of cool. It could be a smudge, a dot, a hole over each letter or word or whatever it is. Again, I have to have the book, but that's pretty doggone cool. And this apparently has started in prison, so pretty doggone cool. A hash function, page 397. So before we even start on hash, a hash, yes, it uses an encryption technique, okay? An algorithm that's kind of based upon that. But the goal is not to hide the message. That is not what these guys are all about. So what this is designed to create a signature on a file so that if anyone made a change to the file, no matter how small, took out one comma, then when I run this hash a second time, the two hash values aren't going to match. So I can tell if somebody's messed with a file by having the original hash versus the second hash. So here's an example of using a hash functions. So I've got an email, for example, from Microsoft. And this is a security bulletin they send out, and they want to make dang sure that no one has messed with it. So this is a PGP signed message. Okay, and they're using a hash algorithm called SHA-256. And so here's the message, the body of the message, and then here is the signature. So this is this massive thing in here that basically tells me all I have to do is just run this through PGP if I wanted to. And it would tell me whether or not anyone has messed with this message, because this is the signature that says everything in here is good to go. All right, making sense? Okay. So one more time to make sure everyone completely understands it. This hash is not something you could take and return the original message back. Okay, it's not designed to do that. It will not do that. Okay, all right, let me just give you a hypothetical that might make more sense. Let's say you're doing, a 16-bit or two bytes checksum on a 15 megabyte file. So I take a 15 megabyte file and I run it through and it produces this simple number, okay? It's only 2 bytes wide, but it's a type of hash. Not a very good one, but that's not the point. The point here, isn't it obvious that if you gave me 2 bytes of information, there is no way in hell I'd be able to reproduce 15 megabytes of data, right? No, absolutely not. Hashes cannot be reversed to return the original. Okay, so let's just talk about one of the things I thought was kind of strange. They have these online hash tools, but let's just look at how many there are. I mean, oh my goodness. They have, of course, also in, in coding and in cryptology, but as far as, how many hash algorithms are out there, here's hash 256. So I type in, Mary had a little lamb. Notice that as I'm typing, it doesn't get any bigger. Why? Because that's not what it's doing. I told it 256, so this is a 256-bit hash of what I'm typing. So if I was to go back and change one letter, okay, kind of pay attention. I'm going to change this B to a D. I mean, they're not anywhere near the same. So this is good way of telling if something has been changed. If I gave you the SHA-256 of Mary Had a Little Lamb, and then somehow it got changed, you'd instantly be able to tell the difference. Okay. Whew. So, the government had a secure hash function using SHA-1, but quite frankly, it wasn't strong enough. And so, again, we're not talking about decrypting it. We're talking about how many other pieces of text can produce that output. In other words, Mary Had a Little Lamb can produce that, but is it possible that some other combinations could also produce the exact same hash, what's called a hash collision? So I really need a very robust hash, maybe one with a bigger key. Okay. So typically hashes don't require keys. I mean, I didn't type in a password. I mean, it's a hashing algorithm now. There are some that will do it and later on we'll be talking about this in detail, where we're talking about I'm using an encryption key to produce a digitally signed email. And yes, I am using a key, but SHA-256, for example, doesn't ask you for a password. So later on, this message authentication code, we are going to use it, but not yet. So one more time. If I give him a hash value, the output of a hash algorithm, can I regenerate the original document? No way in hell. So what's it used for? It's used for the I in the CIA triangle, the integrity. No one has messed with this thing. That's what it's all about. When I download a file, let's say I want to go download, I don't know, a version of Linux, and it's going to give me the hash on the screen. And so after I download it, to make sure nothing happened, I could poke it in here, and it'll tell me whether or not the hash matches. Okay, cool. Okay, Cryptographic Algorithms, page 396. So another way to categorize them, other than being stream and block, is to say symmetric or asymmetric. So this is all about the number of keys. Okay, so symmetric basically means I have a key and I use it to lock my door, and I use the exact same key to unlock my door. I'm not using 2 keys. 1 key does it. 1 key to rule them all. So it's a kind of a simple scenario. I have one particular key. I encrypt the message. It gets turned into that, and somebody uses the exact same key. So it works. I have memorized the key, and you have memorized the key, and so we can send stuff back and forth, and everything works just fine. And as long as nobody else can find the key, you don't have it written down anywhere, you're in good shape. So what's wrong with this approach? Well, it works fairly well with like 2 people. Can you expect Bob to always remember, keep the key private and not write it down? What's the likelihood of Bob getting exposed and having the password leak? But what if you had, okay, I know you send this to 10 people. 100 people? Oh. See how when you add more people, the likelihood of the key getting exposed or written down or something really goes crazy. So private key, yeah. Okay, so one person, yeah, you're okay. All right, so they came up with, the first one that the government came up with is the Data Encryption Standard, DES. And it had a 56-bit encryption key. And that was very suitable back in 1976. Because, man, there were not computers out there that could take a key like this and break the encryption. Okay. But, unfortunately, in today's world, that can be broken in less than a day. Easy. And this is the one I was telling you about that was considered a military secret. This is the t-shirt story. Yeah. So they realized they had a problem, and so they decided to come up with triple DES, and they just called 3DES. So while they were evaluating the replacement, they needed something, a stopgap between what they have and what they were going to get. And so they basically just run DES through 3 times. I mean, it's a little bit more complicated than that, but that's a good enough example. And then they came up with the Advanced Encryption Standard, AES, which is the one that most people are still using. There's lots of variations of it. You can have key sizes that are a different size. And so it's basically free and open source, which is a good thing, and a variable key size. Let's say, for example, I know that I want to make this thing performant as possible, so I use a low key size, maybe 64-bit. And so I send it through, and yes, I know that it's possible that the bad guys can get this and break it within a week. But what if the message has a short-term component, like meet you at noon? Okay, if it takes them 2 weeks to decrypt it, well, too late, right? So things that are kind of short-term, I could use a small key size. And then if it's more important, I could use a huge key size. Okay, so I get to pick this key size, right? That's pretty cool. So Advanced Encryption Standard was cool. Okay, the next one on page 397 is with the asymmetric, which means 2 keys. All right, so I need a pair of keys. I lock the door with 1 key, but I unlock it with another key. It takes 2 to tango. All right, so this one is different. Typically, you don't manage the keys separately, except we're going to be doing, I'm going to be doing a demo with PGP, where I do manage the keys separately. Mostly there's a public repository. For example, if I'm using Microsoft Exchange, and I want to send you an encrypted email, and you work in the same company as me, I just bring you up on my address list. A machine automatically picks the key that you know and I know, the public key part, and does the encryption. So one, key, private key B gets sent across message, and public key B does the encryption. Okay, this is a little complicated to comprehend at first bite, so we're going to go nice and slow, but we're coming up on the 15-minute mark.